Hello everyone, and welcome to the vodcast that is going to help you explain types of chemical reactions. You can find all this information in Chapter 9 of your textbook. Before we begin, make sure that you have your guided notes sitting right next to you as we go through this vodcast. Let's begin. So, just to review a little bit with you, let's talk about the difference between reactants and products when we talk about chemical reactions. And as an example, let's check out water, the formation of water. So water is made from oxygen and hydrogen gas. And when you look at the expression written this way, notice the arrow. Anything on the left side of the arrow we call reactants. Anything on the right side of the arrow we identify as products. And just to review, do you remember the law of the conservation of mass? It says that in any chemical reaction, matter cannot be created nor destroyed. Well, that's going to be kind of important because coming right up, I'm going to teach you something new. There is a number that you can place in the front of formulas that you see inside of a reaction that will help you balance the reaction. Well, why would we need to balance a reaction? Because we want to make sure that when we are looking at chemical reactions, that we are observing the law of the conservation of mass. We need, on the reactant side and the product side, for the atoms, the number of atoms to be the same. So, using my example with the oxygen gas and the hydrogen gas forming water, let's ask ourselves, is this chemical reaction balanced? So, remember to separate mentally in your mind the reactants from the products. So treat those two different sides separately. On the left side of this arrow, we have 2 oxygen atoms and 2 hydrogen atoms. Now let's look at the product side. On the product side, we have 2 hydrogen atoms. Well, that's good, that matches. But we only have 1 oxygen atom. Well, that means that this chemical reaction is not balanced. We are not observing the law of the conservation of mass. So, what do? Well, the way we balance reactions is we use a large number placed in the front of a formula that doubles or multiplies how many compounds you have in the chemical reaction. So, for example, I know I need more oxygen on the product side of my chemical reaction. So how could I do that? Well, a common misconception is that some students, what they want to do when they originally see this reaction is not balanced and they know that they need another oxygen, one of the things that they love to do is to add subscripts. Well, a subscript is a small number placed after the formula. But do you realize that if I place a 2 right here, I'm no longer making water. I just changed the identity of the substance. I just made hydrogen peroxide. This is not allowed when you balance chemical reactions. You cannot change subscripts. The only thing, and this is a law, the only thing that you can do is change the amount of the compounds that you have. And when you first look at this, you're like, well, what would that do? Well, if I place a 2 in the front of the water on the product side, yes, I multiplied everything, which means, yeah, I've got 2 oxygens now. But unfortunately, because I had to place a 2 in front of the whole thing, now I've got 4 hydrogens on the product side. Well, look at your reactant side. You still only have 2. Well, you need 4. But you can balance it. You can multiply stuff on both sides of the reaction. So we did place a 2 here, which, multiplied and gave us 2 oxygen atoms, 2 oxygens, and now we have 4 hydrogen atoms. Remember, treat the reactant side separate from the product side. On the reactant side, right now, I have 2 oxygens. Hey, that matches, right? But I only have 2 hydrogen atoms. Okay, I can balance this reaction by adding more hydrogen on my reactants side. Let's put another coefficient of 2 so that I double up on the hydrogen, which means that I've now balanced the entire reaction. Let's try another one. Balance this one. And what I'm doing here, you'll notice that I do this in most of my, when I balance, is I treat the reactant side separate from the product side. You see my little line that I drew right underneath the arrow? Try to get into a habit of doing that when you practice balancing. So I start off by using something called an atom inventory. It's kind of like a picture that helps me keep track of all the atoms that I have on the reactant side versus the product side. So right now, looking at this, my aluminum is perfectly balanced. But, you know, we have a problem with our bromine. On one side we have 2, on the other side we have 3. So just think in your head, we got to get that bromine balanced. So what's a common multiple? Well, a common multiple for 2 and 3, isn't that 6? So if I wanted to get 6 bromines on this side, what would I have to do? Let's start by trying to put a 2 here. Now if I do put a 2 here, obviously this guy's going to change to 2 as well, and yeah, we got 6. Okay, now let's go to the reactant side. On the reactant side, I know I need 6 bromines. Here's my bromine. If I want 6, you see the little 2 right here, I should probably try a coefficient of 3. Yay! I balanced bromine. But now, don't forget, you got to go back and balance the aluminum too. Well, that's easy. Here's your aluminum. I know I need 2. Let's stick a 2 right here. And sure enough, that corrects this. And now you've got a balanced chemical reaction. Alright, so, let's see, I already got that. There you go. And we're balanced. Yay. Okay, the next section that we're going to teach you a little bit about is the 5 types of chemical reactions. This should be a review for most of you from some of your previous science history, and if not, that's okay. Let's check these things out together for the first time. So, reaction number 1, synthesis. Think about the word synthesize. When you synthesize something, you're usually putting something together or making something. So you'll notice on the left side we have 2 separate entities separated by this plus sign. That means that they're 2 separate things. And then if you look on the product side, we brought them together. We're synthesizing. That's an example of a synthesis reaction. Decomposition reaction. A decomposition reaction means, you know, think about the word, means to decompose or to break apart. So you'll notice on the left side, on the reactant side, you have a compound. But then on the product side, it looks like it got split up. And you see how the plus sign is separating those? The next type of reaction, single replacement. A single replacement reaction is pretty easy to identify. What you're usually going to have, as you can see right here, is some kind of compound. You see how it's brought together and there's no plus sign separating it, so that means it's a compound. And then you see a plus sign, and then you see the single thing sitting here by himself. That's probably an element. And remember, elements can be diatomic gases or, you know, metals that are perfectly stable sitting by themselves. But you'll notice in the product side, it looks like we switched, right? This used to be AB, and now, well, it's AC. Notice the next reaction is a double replacement. In a double replacement, you have a complete overhaul of what you started with on the reactant side. So over here you have a compound and a compound. Notice on the product side, they're 2 totally different compounds. So one of the questions that I always get about the single replacement reaction is, hey, Mrs. Crowley, you see on the product side, you have AC. Well, couldn't it also be, you know, instead of AC, couldn't it be like C and B matching up instead? Absolutely. So if I were to rewrite this on the product side, you see my arrow, if I were to rewrite my products to say CB, and then it is A that got kicked off, can you have that? Absolutely. Single replacement reactions, the way I wrote it here, you'll notice that the B is written second in the compound, and then I replace it with the C. Well, you know how in chemical formulas like ionic formulas, we always write the metal first and the nonmetal second? Well, this particular single replacement reaction, the way I wrote it, would mean that the nonmetals are switching. But now, let's look at the other one that I wrote. The other one that I wrote over here is a little bit different, the way that I wrote it. So you'll notice that instead of the B and the C switching, I switched the A with the C. What that means is that you're switching, because this is kind of like an ionic compound, we always write metals first. I switched it as if C was acting like a metal, and you'll notice that I wrote the C first in the formula and the B second. I didn't say BC, I said CB. So in single replacement reactions, you can either switch the metal or you can switch the non-metal, and we'll talk a lot about that later. One more chemical reaction, and I saved the best for last: combustion. So in a typical combustion reaction, oxygen gas is combined with some kind of substance, and it's usually associated with a release of energy in the form of heat and or light. So it says typically these reactions take place with something called hydrocarbons. Break down this word. Hydro, hydrogen, carbons, obviously carbons. So these are compounds that basically contain hydrogen and carbon, but they sometimes contain oxygen in them as well. So here's an example: carbon and hydrogen, CH4. This is a hydrocarbon, and you'll see oxygen being added. You didn't even have to tell me anything about the product. You should be able to predict the products of a combustion reaction, even if they're not given to you. In a typical combustion reaction with a hydrocarbon, you will always, yes, I said always, make carbon dioxide and water. And in a combustion reaction, if you see the products are carbon dioxide and water, you'll know that you've got a hydrocarbon being added to oxygen. These are, in my opinion, are one of the easiest types of reactions to identify. Let's go back to single replacement reactions and talk a little bit more about when single replacement reactions work. Sometimes you've got a sticky situation. They're a little bit tricky. They will only work under certain conditions. When a compound that is dissolved in water, so let's think about a compound. A compound is a metal and a nonmetal dissolved in water. When you introduce a different metal into the solution, sometimes the reaction will work, but sometimes the reaction won't work. How do you know? Well, we need to make sure you understand that there is something called a metal reactivity. And there's also a separate nonmetal reactivity. It basically lists every metal and every nonmetal on a different sheet in order of how reactive it is. And that will tell you whether or not the reaction will work. You can find the metal reactivity on the back of the periodic tables that I provided you in class. So, if the element, the single solo element that you introduce into the solution, isn't reactive, well, then the reaction is not going to work. So to give you a better example of this, let's take an example here. So this is the solo metal that you are going to throw into a solution, and the solution has sodium and chlorine. You can kind of think of this as these guys are dancing on the dance floor. This is like, the studly guy, and this is the flirtatious girl, okay? And just like in real life, this will make you laugh. Just like in real life, the girl could look around the dance floor for a hotter guy. And sure enough, a guy comes out onto the dance floor. Magnesium is coming out on the dance floor. This combination, this dancing couple, will only split up if magnesium is a hot stud. Okay, so in other words, we're hoping that magnesium is more reactive than sodium. Well, is it? You're going to have to check the metal reactivity series. So let's take a look. Magnesium is located here, and sodium is located here. And this is totally in order. High reactivity is up here. This is highly reactive. And down here, this is very low reactivity. So it looks like chlorine already has a pretty hot stud. Chlorine's already got sodium. And magnesium is the guy that's trying to cut in. I don't think so. This reaction is not going to occur. Let's try a different example. Now, who is the couple dancing on the dance floor? So there's a pair that is already stuck together and dancing. It is magnesium and chlorine. So it's the same situation. You have a metal coming out onto the dance floor trying to cut in. So we need to check the reactivity of calcium. Now, if calcium is more reactive, more studly than magnesium, well then chlorine is going to break up with magnesium and take a new partner. So let's check. We're looking to see if calcium is higher in reactivity than magnesium. Oh, here's calcium. And here is magnesium. Sure enough, calcium is higher in reactivity than magnesium. So this reaction will work. So what does that mean? Well, they're going to switch partners. Okay? So imagine in your head these two switching spots. But when you do switch them, you need to make sure that you're rebalancing the charges on the product side. And I gave you an easy one, a lucky one, because magnesium and calcium both are positive 2. But what if I had a metal that had, say, like a positive 1 charge? Notice this is a balanced ionic formula. So be careful when you switch them that you are rebalancing the new ionic compound that is formed. So you'll see magnesium gets the boot. He is solo now. He's by himself. He got the boot. And the new couple, calcium and chlorine, are brought together. Now let's try some different single replacement reactions where you have to react with either water or an acid. So pretend in your mind's eye, think about this, you are dipping a metal in either water or an acid. And we need to check the reactivity. Okay, so it's pretty easy to think about who the couple is when you're looking at either water or an acid. An acid is easy. There's your couple. You've got the hydrogen ion on one side, and on this case you have the nitrate ion on the other side. Acids are easy to see. But what about water? Well, let's take it one step at a time. Let's treat each example separately. So the very first one that we have is calcium. Calcium being introduced to nitric acid. So here's calcium, and you'll notice the box next to it says that it reacts with water and acids. So this reaction will work. In fact, if you stick calcium metal in an acid, you're going to get a pretty vigorous reaction depending on the strength of the acid. So in the first reaction, we definitely have a good situation. This reaction will work. So when you pop off the hydrogen from the acid, what does that mean happens in your product side? Well, calcium and hydrogen are going to take a switch. But then what happens to the hydrogen? Because the hydrogen is going to be by himself. Guys, if hydrogen's by himself, you have to make it hydrogen gas. We can't have a single hydrogen atom sitting by himself. So when hydrogen gets the boot from an acid, you'll make hydrogen gas. And notice I had to rebalance the charges of my new compound. Calcium is positive 2, and nitrate is negative 1. Make sure you're always rebalancing the new ionic compound. Now let's look at water. Calcium replaces hydrogens from acid and water, so I know that this reaction is going to work too. But water's a little bit weird. We need to make sure that you remember that hydrogen should be treated as a hydrogen ion attached to a hydroxide ion. That'll make it easier for you to visualize, because calcium will replace the hydrogen, right? Well, okay, the hydrogen gets popped off, still making hydrogen gas. But now you've got to match calcium together with hydroxide. And you'll notice that I did balance my charges just like I did the last time. So, metals reacting in water will make, 100% of the time, metal hydroxides. Pretty cool. Now we're going to go back and look over one more time double replacement reactions. So double replacement reactions, just like single replacement reactions, are kind of tricky. They will only go under certain circumstances, and there are 3 circumstances that will make double replacement reactions work. Number 1, you make a gas. Anytime you make a gas, the reaction's going to go. Number 2, an insoluble product is produced. Now I want to think about this word, insoluble. Soluble means that something dissolves in something, right? Insoluble means it does not dissolve in something. And that something for us, when we're talking in chemistry, is usually water. So water solubility, we'll talk about that in just a minute. And in case number 3, if you make a pure substance with no charge, typically this means we're talking usually about water. There's a couple others that we'll talk about when we get to those. So, first thing that we have to learn are some solubility rules. Remember that periodic table that had the metal reactivity series on it? Well, take another look. On the back of the periodic table, you'll also know that I have something on there called the solubility rules. Alright, did you know this? That not all ionic compounds that you place into water will dissolve? Some substances have such a strong ionic bond that not even water can break them up. So let's go ahead and give it a try. Use your solubility rules on the back of the periodic table to try to predict whether or not the following are going to dissolve. Your first problem is calcium nitrate. Try to find the rules for nitrate ions. Read all the way across. The rule states that all nitrate compounds are soluble, with no exceptions. This means that this guy right here is able to dissolve. This is soluble. Let's look at the next example, calcium hydroxide. Try to find the rules for hydroxide ions. You'll notice that in the rules for hydroxides, you're on the bottom half of the solubility rule table. The bottom half switches from soluble to insoluble. Go ahead and read all the way across hydroxides. It says, all hydroxides are insoluble, except those of alkali metals. Alkali metals are the first group on the periodic table: lithium, sodium, potassium, rubidium, and calcium, strontium, and barium. So normally, hydroxides are insoluble, but this rule states that calcium, as well as strontium and barium, is an exception to the rule. So, instead of saying that this is insoluble, we're going to say that this is soluble. Let's look at number 3. You have sodium carbonate. So go ahead and try to find the rules for carbonates. It's on the bottom half of your solubility chart. It says all carbonates, sulfites, phosphates, and chromates are insoluble except those of alkali metals and ammonium. Hey, check it out. Sodium. Well, sodium is an alkali metal. So instead of saying that this guy is insoluble, you have an exception to that rule. This is another soluble compound. Try number 4 this time. You have a carbonate again, and Fe is iron. Well, it says all carbonates are insoluble, but you want to check for any exceptions. Is iron an alkali metal? Absolutely not. Finally, you found one that is insoluble. This is a recap of all the things that I just told you. One of the things that you should know is the symbol for soluble. The symbol for soluble we label AQ, and this means aqueous. Think about my little bit of Spanish here. Think about the word agua. Most people know that that means water. So the symbol AQ and the word aqueous came from aqua, AQ. Aqueous means able to dissolve in water. Alright, now let's put this new rule, solubility rules, to good practice. Let's take a look at 2 different double replacement reactions and how we would determine whether or not the reaction works and predicting their products. Step number 1, check the solubility of each reactant first. So go to your solubility rules on the back side of the periodic table, and let's check and make sure. Here you have sodium sulfate. Check your sulfate rules, but as a general rule of thumb, if you ever see an alkali metal in the front, you can pretty much guarantee that this is going to be soluble. And what's the symbol for soluble? AQ. Let's go to the next one, calcium nitrate. Look up the rules for nitrates. The rule for nitrates says that all nitrates are soluble, no exceptions. Let's go to the second problem, magnesium nitrate. Do you still remember the rule for nitrates? All soluble, no exceptions. Let's check on this calcium chloride. Find the rule for chlorides. All chlorides are soluble except silver, mercury, and lead. Alright, well we don't have silver, mercury, or lead, so I know that this guy is soluble. Why is step number 1 important? Step number 1 is important so that when we talk about chemical reactions dissolved in water, all of the ions have to be able to move around in solution. And if they're locked up because they're not soluble, well, it's going to be really hard for that reaction to work if the ions aren't able to flow freely in a solution. In other words, dissolve. The next step, step 2. Let's switch partners and try to predict our products. So in the first example, you have sodium sulfate, calcium nitrate. So sodium doesn't want to be with sulfate anymore. We're going to hook up sodium to the other anion, the nitrate. Right? And we've got polyatomic stuff, so it's kind of hard to visualize. So one of our products is going to be sodium nitrate. The other product is going to be from this guy coming over to sulfate. So we're basically switching all the partners. Don't ever switch a metal with another metal because, you know, sodium makes a positive ion, but calcium makes a positive ion too. And when you get two positives next to each other, that's not going to work. So our products over here, calcium sulfate, do you have to worry about balancing charges? Yes. So when you make ionic compounds on the product side, always check that you are balancing your charges. Alright, so we have calcium sulfate, sodium nitrate. I did the same thing over here. Magnesium is going to switch partners and be with chlorine. Calcium will switch partners and be with nitrate. Notice I balanced my charges here because magnesium is positive 2, chlorine is negative 1. And I had to do it again over here too. Calcium is positive 2, nitrate is negative 1. Next, step 3, you need to balance the reaction with the use of coefficients. Alright, back over on the first reaction up on top. You have two nitrates. You see the NO3s and you see the little 2? You have two nitrates on the reactant side, and here's nitrate on the product side. Do you understand why I had to put a 2? And notice that gives me two sodiums, right? Well, lucky me, I had two sodiums on the reactant side. So this is perfectly balanced now. The second reaction, you got lucky. It's already balanced. The next step, we are going to do the final and last step. Check for solubility. Because remember, these reactions are only going to work if you make one insoluble product. One product that does not dissolve in water. Well, I don't know if you remember this, but the fancy word for an insoluble product is precipitate. Do you remember that word? Precipitate. That is the solid product in a, when you start with like two liquidy solutions, if you make a solid product, we call that your precipitate. So in the first reaction, I checked my solubility on my products, and sure enough, I found one that is insoluble. But notice on the second reaction, everything is soluble. In other words, we didn't make a really good hookup on the second reaction. Nothing actually wanted to hook up together. That reaction doesn't work.